Welcome, everyone, to our third session of the Future of Work, Day 2 in the MIT AI Conference. I'd like to welcome Ion Stoica, who is the co-founder and executive chairman of Anyscale and Databricks, and also a professor in the EECS department at UC Berkeley, who will be discussing the future of computing is distributed with us today during the conference. Ion, welcome and thank you. I'll hand it off.
Thank you. Thank you very much. Very glad to be here. Hello, everybody. So today I'm going to talk and I'm going to make the argument that the future of computing is distributed. Now, distributed computing is not new. Almost every decade, a new category of application has become distributed. Arguably, the first distributed system was the ARPANET, the precursor of today's internet, started in early 1970s. This gave researchers the ability to access powerful computers across the United States. This also led to the creation of the email by Ray Tomlinson in 1971. In 1980, saw the emergence of high-performance computing. The first high-performance computer partnership, or HPC, began in 1985 when the National Science Foundation established a partnership with 5 US universities. This led to powerful simulators, which allow engineers and researchers to build airplanes, do weather forecasting, and molecular modeling. 90s saw the rise of the web and the internet. This led to building highly distributed systems to support popular websites, which are accessed by tens of thousands to hundreds of millions of users. The design patterns here, including LAMP stack and the emergence of microservice architectures. In 2000, we saw the emergence of the big data. As the internet companies were amassing huge amounts of logs, they wanted to get a better understanding of their user behavior to improve this user experience as well as their businesses. This led to the creation of massively distributed systems to process this data, such as MapReduce and Spark. So, as you can see over the year, more and more workloads became distributed, and once these workloads became distributed, they remain distributed. However, despite all these developments, distributed computing is still an exception today. Few developers program distributed applications, and in part this is because it's very difficult to develop these applications. And actually, relatively few universities teach distributed programming. However, we argue this will change. That is, distributed computing will become the norm rather than the exception. So what is different this time around? Why will this happen? 3 reasons. The rise of deep learning. Second is the end of the Moore's law. And the third is more and more applications are becoming AI-centric. This is by now a famous plot from OpenAI from last year, which shows the compute requirements to train the state-of-the-art deep learning models. The plot, the y-axis, is the log scale. And basically what this shows from 2012 to 2019, then the computation demands to train the state-of-the-art deep learning models increase 35 times every 18 months. And here I pick 18 months because this used to be the time period over which the computation performance of the CPUs doubled. And this is not true only for esoteric application like AlphaGo to play Go or other games, but also for very practical application like natural language translation and image processing. Actually, as you can see, for this kind of applications, the slope of increase, the slope which the demand increases is even steeper. And it's not only the processing which is growing leaps and bounds, it's also the memory. This plot shows the number of parameters in some of the premier and the state-of-art models which have been released over the last 4 years. And again, the y-axis is a log scale. And as you can see, starting from 2016 until this year, the number of parameters of the state-of-art models increased 20 times every 18 months. And if you look only at the past years, this increase is much, much bigger, 200 times every 18 months. So the second trend we've been seeing now for more than 1 decade is at the end of the Moore's law. So this is a plot showing the performance of the CPUs, of a core on CPU, over the years. And you can see the green regions here. It was the heydays. It was when every 18 months, the processor performance doubled. So that was what was used to now or to be known as Moore's law. And now to put things into perspective, is going back to our plot of the computation requirements of the state-of-the-art models. Here, however, the Moore's law sits, and here where the CPU performance increase sits in this plot. So you can see there is a huge gap opening between the demands of these deep learning models, the training deep learning models, and the CPU performance. Actually, even if the Moore's law hadn't ended, it will still fall way short of satisfying the demands of these machine learning applications. Now, you may ask, what about specialized hardware? As you know, over the past two decades, a lot of specialized hardware in the form of GPUs and more recently TPUs, TensorFlow processing unit, have been released. And these processors, they do improve the performance by trading generality for performance, so focusing on a particular workload, for instance, training machine learning model very efficiently, at the expense of supporting more general applications. Well, it turns out that this specialized hardware is just prolonging the Moore's law. They do not really solve the problem. And to illustrate this point, this is where GPUs and TPUs are on the same plot. And yes, they are much more powerful. So than the CPU. However, their growth still follows more or less the Moore's law. So this means they are still far from being enough to close a gap to the demands of deep learning applications. And this gap is just increasing. And obviously, this is also true for memory. For the past four years or so, the GPU memory increased by just approximately 1.5 times every 18 months, when the size of the model increased again 20 times or more over the same time period. So really, when you put this together, you can see that in order to support these workloads, there is absolutely no way but to distribute these workloads, to using multiple machines to run these workloads. The final trend is that these AI applications are becoming distributed. And not only that, but they are also the applications are becoming more AI-centric. So indeed, virtually every application today is incorporating now elements of AI, including e-commerce, financial application like fraud detections and forecasting, manufacturing, healthcare, and many more. So this means that these distributed workloads are no longer isolated. Indeed, it used to be, and is still the case today, that different workloads are running separately using different software stacks. For instance, the software stack for HPC is quite different from the software stack for the big data, which is quite different from the software stack to run microservices, which is quite different than the software stack for deep learning. However, we are already seeing workloads coming together. First, AI, it's already overlapping with HPC. Indeed, distributed training systems like Horobot are already leveraging MPI, a system developed by the HPC community for the past 30 years. Similarly, some industrial reinforcement learning applications are leveraging large-scale simulations running on HPC clusters. Second, AI and big data are strongly overlapping, as most AI applications today need huge amount of data to train sophisticated models. Finally, the microservice architectures that power many of today's services is starting to integrate machine learning components, as these services are leveraging more and more AI to improve their user experience. However, despite this convergence, so in summary, we've seen that there is no way to scale the deep learning applications by going distributed. And this is because the gap between these application requirements and the capabilities of a single node or a single processor are growing faster than ever. At the second time, we've seen that the AI is becoming pervasive. It's becoming part of virtually any distributed applications. So when you put all this together, then this leads to the conclusion that distributed application will become the norm. Now, despite this convergence, systems used to support these different workloads are still as diverse and distinct as ever. For instance, for deep learning, we have systems like TensorFlow, PyTorch, Horobot, and others. For microservices, you have Django, Spring, Go, and other frameworks. For big data, you have Hadoop, MapReduce, Apache Spark, Flink, and Kafka. And for HPC, like I mentioned, you have MPI. So it's again, here you have a lot of great systems, but each system is targeted to a particular workload. Okay? But ideally, what we need is a general purpose distributed framework to support all these workloads. And this is exactly the goal we set up for ourselves when we started to build Ray, a general purpose framework for Python and Java. We started this effort 4 years ago. And just to say a few words about Ray and put another perspective on the problem we try to solve, again, today, like we've seen from this presentation, building an AI application requires to support multiple workloads. And to support these multiple workloads in the same application require us to stitch together a zoo of systems, training systems, model serving, simulation systems, streaming systems to get data and process it in real time, featureization to get great feature for our models, to tune our models, and many more. And again, for each of these particular workloads, we do have great systems. But in order to build an end-to-end application, we need to stitch together these systems. And this is very hard because different systems can come with different APIs. So therefore, it's hard to develop, hard to test, it's hard to deploy, and to manage multiple systems stitched together. So what Ray provides a general execution engine, which sits at the core. And this is a foundation on which you can build very powerful libraries, which can support all these workloads. So now you have only one system which can support these end-to-end AI applications. And we already built some powerful libraries like RLib for reinforcement learning, Tune for hyperparameter search, and Serve for serving. And there are many other third-party libraries being now developed on top of Ray. Ray, its experience is an open source project which experiences a very fast adoption rate. Today, it has over 12,000 GitHub stars, over 300 contributors, which are coming from more than 50 companies. It's included in the Azure Machine Learning, and it's also available in AWS SageMakers. And it's used by many companies today, in many cases in production. Also, I'd like to take this moment to let you know and invite everyone to the Ray Summit. This will be the first summit. It will be on September 30, from September 30 to October 1st. And it will be like this event. It will be online and it will be free. So hope to see many of you virtually there. So in conclusion, as I hope, that I convince you we are at the dawn of the new exciting era in computing. And this era will be driven by the fact that distributed applications are going to become the norm rather than the exception. Today, building this distributed application is super hard. It requires rocket scientists, experts to build those. So the holy grail is to make the programming this and building applications, programming your clusters as easy as programming your laptop. And Ray, we believe, is one of the first step to realizing this vision. Thank you.
Ian, thank you so much for that presentation. We all look forward to attending the Ray Summit at the end of the year. Thanks for informing us about that as well. Right now, we don't have any questions. I don't know if there's anything else you'd like to expand on for the last couple minutes, or hopefully somebody will type in a question as well.
Yeah, I think, you know, I'm just going to reiterate a few things I mentioned, and basically it's again, these are very exciting times, and we never seen in the history an increase in the demand of the computation from some applications as fast as we are seeing today. It's like an application, you know, we used to, the Moore's law, you know, powered the entire computer industry for the past 50 years or more. And that was driven by the fact the capabilities of the processor, the performance of the processors was doubling every 18 months. And that was during the heydays. So doubling every 18 months. And now we are seeing applications whose demands is increasing it's twice every 18 months, but 20 times, 30 times, 200 times. And that's what you are seeing. And you are seeing right now this kind of huge cluster being employed to train these models, to implement these applications. You know, you can see people training models, and the training alone costs, you know, tens of thousands of dollars, hundreds of thousands of dollars, even, you know, maybe millions of dollars for the largest models. And this again is like when it's a huge challenge, and obviously that, you know, big challenges open big opportunities. So that's what is so exciting about. And if you think about that, again, one way to alleviate and to address this challenge, it's basically, okay, one node cannot support this application, so you have to put multiple nodes together. You need to put the cluster together. But fundamentally, while you have this available in the cloud, or you know, you may have, you know, some large companies have very large clusters. Programming this cluster is super, super hard, right? And we do not teach enough of those at school, at universities. And I think this has to change, because if almost all the applications will have to run on multiple machines, and you know, you need to have almost everyone being able to develop this application, otherwise you are in trouble. And in order to have that, to open this, you know, and making available all this power to, you know, to domain experts, to programs which are not experts in distributed computing, you need to lower drastically the barrier of entry, so to speak, to program and to build these applications. So that's, I think, in a nutshell, what it's, you know, it's what I wanted to convey during my talk. And yeah, I'm looking very much forward, and I think that we are going to see a lot of very exciting developments over the next 5 to 10 years.
Great, thank you for that. We actually do have a couple more, 4 or so questions. Let's see how much we can get through in the next 5 minutes. What is the largest system you've implemented, and how fast did it come together? Productivity, and where does that system run?
Yeah. So the largest, okay, so the largest systems we implemented, I was part of it. This is happening at Databricks, which was, is a company behind Spark. It's another, a big data processing framework, which is now is a standard in the big data processing. We developed also at Berkeley, and this at Databricks. So we are running there millions of computer instances at any given time. Of course, they are not employed for a single application, but they are employed by, by many, many users, thousands of users, each of them is their own cluster. With respect to Ray, this is a newer system. And the largest cluster we are aware of, which it's not ourselves running it, it's over 1,000 nodes, and it's used to dramatically improve things like recommendations, so ability to update the models and deploy it in production in a few minutes instead of hours. And this is deployed at a large fintech company.
Got it. Wonderful. Thank you. Is the placement and movement of data the main constraint in the ability to do distributed computing, a connectivity and bottleneck issue?
I think from the performance, yes, this is, well, there are, from the performance, yes, it's one of the main bottlenecks. However, the speed of the network increases very fast. But it turns out to be a real bottleneck. It's also related with the data, but it's not necessarily about the movement, but ingesting the data. Because ingesting the data requires to read the data, which has different needs, come in different formats. And the overhead of just this process is called serializing and deserializing the data. You need to get the data from somewhere and transform it into a format which is understood by the program. And this is actually a huge overhead. And also this is going to impact the processing requirements. In many systems, this is one of the main overheads, and not necessarily moving the data from between the nodes. But the other overhead, and I think the biggest barrier, is actually to build this application, to program these applications. The application, and because a distributed system is fundamentally more difficult because you have to deal with multiple, it's like you need to keep multiple balls in the air, right? One machine goes wrong, that can impact the entire system. You have, and the larger the system, the bigger the problem is. That, it's like the chance that if you have, 1,000 nodes, that one node actually to fail per day, it's very high. So at any given time, so this is, it's like the failures become a norm rather than the exception. When you run on your laptop, you don't think that it's going to crash or going to fail. So from time to time it's going to crash, but it's like that's not in your plans. But when you build this kind of application, it must be in your plan. There's some kind of nodes will fail at any time. There's some of the nodes will become slow and things like that. And even without that, trying to synchronize and to move data, it's very hard. It's like all of us, and this is because the human mind, it's much, we are trained to deal with sequential things, but when things are going in parallel, it's much harder. Imagine yourself that you need to handle 5 things or 5 jobs at the same time. It's very hard.
Yeah, it does sound hard. Great. Well, we have 1 more minute. How about the question from Simon D? Can you talk about how computation requirements are evolving on the inference side as opposed to training, and what implications, especially, that has on mobile devices?
Yes. So this is great. So all the plots, great questions. All the plots I've shown are from the computation or the training side. And obviously, once you train a model, then you serve the model. And I discussed a little bit about serving, but I didn't show the plots about the overhead on the serving. Now, one proxy for that is the size of the model. The size of the model, as you've seen, they grow as fast, if not faster, than the computation, at least in some cases. So you should expect that the inference demands will grow. The growth will be, the same ballpark. Now, with the inference, what you can do though, there are many, there are more techniques to take the model and to compact it, to use lower precisions, so to reduce the demands. And then, there are, so that we have, because it's a simple process, the inference and prediction actually, the simpler process. It's easier to be smart about the algorithms, about architecture of the models. So once we train them, to squash them and to make them smaller. And that's a very active area of research, and obviously it's critical if we want to push them on our phones. And that's critical because that's to preserve and the privacy of the users. So that's, again, it's it's
wonderful. Well, thank you so much again for your time and telling us about your research. We greatly appreciate it.
Thank you.
Yep. And for all the listeners out there and viewers, we will be joining in a few minutes on the next session. Thank you for your time.